The universe is a vast and mysterious place governed by laws that we are only beginning to understand. Among these, the second law of thermodynamics stands out as a profound and often misunderstood principle. Simply put, it states that the total entropy of an isolated system can only increase over time. In other words, disorder always increases. While seemingly straightforward, the second law has sparked debate among physicists and philosophers alike. Some question its absolute nature, suggesting that it might not be a fundamental law but rather a result of other, more basic principles. This skepticism arises from the probabilistic nature of entropy, leading some to believe that a decrease in entropy, though statistically unlikely, is not impossible. Could the universe, in a rare cosmic roll of the dice, rewind its own disorder? These doubts often stem from comparing the second law to other fundamental laws like Newton's laws of motion. These laws seem deterministic, painting a picture of a universe where every action has an equal and opposite reaction, where the trajectory of objects can be precisely calculated. The second law, with its focus on probabilities and the tendency towards disorder, appears to clash with this deterministic view. However, as we delve deeper into the nature of entropy and its implications, we'll discover that these criticisms, while understandable, are ultimately unfounded. The second law, far from being a cosmic accident, is a fundamental truth about our universe, guiding its evolution from the Big Bang to the eventual heat death. The heart of the debate surrounding the second law lies in the concept of probability. Critics argue that entropy, a measure of disorder, is inherently probabilistic. It's not that things cannot become more ordered, just that it's statistically improbable. Imagine a deck of cards, perfectly arranged by suit and number. Shuffle it once and the order is disturbed. Shuffle it a million times and the chances of returning to that initial perfect order become astronomically small. This probabilistic nature, critics argue, leaves room for doubt about the absolute nature of the second law. Couldn't random fluctuations, however unlikely, lead to a spontaneous decrease in entropy? Perhaps a spilled glass of water could reassemble itself, defying the expected increase in disorder. Maybe, in a universe vast enough, pockets of decreasing entropy exist, defying the universal trend. Furthermore, critics point to the apparent contradiction between the second law and other fundamental laws of physics, particularly Newton's laws of motion. These laws are time reversible. If we film a ball rolling down a hill and play it in reverse, the ball's motion obeys Newton's laws perfectly, regardless of the direction of time. Yet, the second law seems to impose an arrow of time, dictating that systems tend towards disorder as time moves forward. This perceived conflict fuels the debate, leading some to question whether the second law is truly fundamental or merely a macroscopic consequence of more fundamental time-reversible laws at play. If the universe operates on deterministic principles at its core, how can a law based on probability hold such sway? While the probabilistic nature of the second law might seem like a loophole, a way to challenge its universality, it's actually the key to its strength. The universe, as we observe it, is not a small, isolated system. It's a vast and complex entity, teeming with interactions at every level. To illustrate, let's return to the card analogy. While shuffling a deck once might not guarantee complete randomness, shuffling it repeatedly makes the odds of returning to the original order vanish. The universe, in its vastness and constant activity, is like that deck of cards being shuffled trillions upon trillions of times each second. The sheer scale tips the scales of probability, making any significant and sustained decrease in entropy statistically impossible. Furthermore, while isolated instances of decreasing entropy might occur on a small scale, they are always outweighed by larger increases in entropy elsewhere. The spilled water might reassemble itself, but only at the expense of a greater energy input and increase in disorder in its surroundings. The house always wins. Even apparent violations of the second law ultimately prove its resilience. The perceived conflict with Newton's laws also dissolves upon closer examination. While these laws are time reversible, they don't dictate the direction of time's arrow. The second law, on the other hand, introduces this crucial element, explaining why we experience time moving forward, from a past of lower entropy to a future of higher entropy. Entropy, often described as a measure of disorder, is a concept that can be difficult to grasp. A more accurate, though perhaps less intuitive way to think about it, is as a measure of a system's spread-outedness, or the number of possible arrangements of its components. Imagine a pristine, perfectly arranged library. Each book is in its designated spot, the epitome of order. Now, imagine a tornado ripping through the library, scattering books haphazardly. The library is now in a state of high entropy. There are countless ways the books could be arranged randomly, but only one way for them to be perfectly ordered. This increase in entropy isn't just about physical disarray, it also applies to energy. Usable energy, like the fuel in your car, is concentrated and organized. As it's used, it dissipates as heat, a less organized form of energy spread across a wider area. Entropy's significance lies in its universality. It governs everything from the formation of stars and galaxies to the functioning of our own bodies. The second law tells us that the universe is engaged in a constant march towards greater entropy, a journey from which there is no turning back. The second law of thermodynamics plays a crucial role in understanding not just the present state of the universe, but also its past and future. It provides insights into the universe's initial conditions and sheds light on its ultimate fate. The Big Bang, the event that birthed our universe, is believed to have started from a state of exceptionally low entropy. All the universe's energy was concentrated in a single point, an incredibly ordered state. From that point onward, the second law dictates that entropy has been steadily increasing, driving the universe's expansion and the formation of stars, galaxies, and planets. Looking towards the future, the second law paints a picture of the universe's inevitable heat death. As entropy continues to increase, usable energy will become increasingly scarce. Stars will exhaust their fuel, galaxies will drift apart, and the universe will approach a state of maximum entropy, a uniform sea of low-energy particles where nothing much happens. However, this doesn't mean the universe will be devoid of beauty or complexity. Life, as we know it, thrives on gradients, on differences in energy and temperature. The journey towards maximum entropy is not a descent into chaos, but rather a transformation, a continuous exploration of new possibilities within the constraints of the second law. The development of quantum mechanics in the 20th century introduced a new level of complexity to our understanding of the universe. The seemingly random and counterintuitive behavior of particles at the quantum level raised questions about the universality of classical laws, including the second law of thermodynamics. Could the probabilistic nature of quantum mechanics provide a way to circumvent the second law? After all, if particles can exist in multiple states simultaneously and tunnel through energy barriers, couldn't they potentially defy the expected increase in entropy? While the relationship between quantum mechanics and thermodynamics is still an area of active research, the second law appears to hold firm even in the quantum realm. While quantum fluctuations can lead to local and temporary decreases in entropy, these fluctuations are always balanced by increases elsewhere, preserving the overall trend towards greater entropy. In fact, some interpretations of quantum mechanics suggest that the second law itself might play a role in the collapse of wave functions, the process by which a quantum system chooses a single state from a superposition of possibilities. This intriguing connection hints at a deep relationship between the two, further solidifying the second law's place as a fundamental principle governing the universe at all scales. The second law of thermodynamics, with its inexorable increase in entropy, might seem like a bleak prophecy, a cosmic death knell for the universe. However, it's important to remember that life itself is a testament to the second law's power. Life exists because of energy gradients, the differences in temperature and energy that allow for work to be done, for complexity to arise. We consume energy-rich matter and release heat, contributing to the overall increase in entropy, while simultaneously creating localized pockets of order. The second law doesn't preclude the existence of life, it simply dictates the terms on which life can exist. It reminds us that our existence is precious and finite, a fleeting moment in the grand cosmic dance of energy and entropy. The eventual heat death of the universe, though perhaps billions of years away, is a sobering thought. But it also serves as a call to action. It compels us to cherish the time we have, to explore the universe and unravel its mysteries, to create meaning and beauty amidst the ever-increasing entropy. The second law is not a harbinger of doom, but rather a guiding principle, a reminder that our existence is a delicate balance, a testament to the universe's ability to create order from chaos, even as it marches towards its ultimate fate. It's a story written in the language of energy and entropy, a story that we, as sentient beings in this vast and ever-evolving cosmos, have the privilege to witness and explore.